And we're recording. Okay, good afternoon and welcome to SEMC's Winter Spring EM course. Today our guest lecturer is Joachim. He's a professor at Columbia University. He's highly regarded for his seminal work on ribosomes as well as single particle cryo-EM. He made a lot of his significant contributions towards the structure and function of ribosomes when he was at the Wadsworth Center at SUNY Albany. He has many awards, including the Benjamin Franklin Medal of Life Science in 2014, the Wiley Prize in 2017, the Nobel Prize in Chemistry in 2017, which he shared with Jacques Dubuchet and Richard Henderson. And in 2018, he's also an honorary fellow of the Royal Microscopy Society. He also is a very accomplished author, and if you're interested, you can see his books at a virtual bookstore near you. So thank you, Joachim, for coming today in our Cryo-EM course. So let's start off and with a little bit of background. And how did you get into, I should parse this question, not only cryo-EM, but electron microscopy?
Right, because there was no cryo-EM when I started. So I got into it as a physicist and developed an interest in electron microscopy during my master thesis, and then choose a group that was working on electron microscopy in Munich. And that group was Walter Hoppes. And he had a very interesting vitae. He was an X-ray crystallographer and developed a late interest in electron microscopy. So he's essentially turned his entire interest to electron microscopy. And in his mind, it was a very challenging kind of area to get into. And in his mind, electron microscopy was essentially X-ray crystallography, where you get the phases for free. Okay. So this is how I got started. So I just want to stress that right at the beginning, the was sort of built in. It was also Hopper had a very close relationship with Max Perutz at the MRC, and they jointly organized workshops in the winter in the Alps, in the Austrian Alps, that brought together groups from protein crystallography and the nascent smaller groups from electron microscopy. There was a very early interaction and exchange of concepts. And so that's how it all started.
Do you happen to have a favorite microscope when you first learned electron microscopy?
A favorite microscope? I wouldn't say. I stayed away from electron microscopes really because I discovered early that I didn't really have a good hand with it, a good thumb. So I sort of stayed on the theoretical and analytical side.
How has the field changed over the years in your mind? Because you've been in the field for several decades.
Oh, there has been huge changes, of course. At the beginning, electron microscopes were really not made for looking at molecules. There was always a race of getting higher and higher resolution, but electron microscopy was really only used for looking at sections and rather, to my mind, very boring stuff. And then when and it really took a while until instrument companies thought that there was a market for real high resolution structure research. And of course, it was very much accelerated after the invention of the cryo techniques by Jacques Dubuchet and others. And then it sort of took off, and the electron microscopes became specialized in cryo methods. It really had implications, lots of implications for vacuum design and for everything, and for the entry, the kind of sample entry systems. And then the very big jump occurred when field emission guns were introduced. That was sort of in the 90s, and then they became sort of standard part of the instrument. Field emission guns meant that you could get very high coherence, and you wouldn't sort of be defeated by the envelope function. And then another jump occurred through what was this? Well, the very big jump occurred with the introduction of computational control. Computational control and image collection was really paired up in the microscope. This was the so-called techni a direction of the microscope, and it was really FEI, which was the precursor of Thermo Fisher, that took this seriously right at the beginning, and that explains the big lag of JOL, who really followed this development with some delay. And that's why FEI has gotten so big in the whole field, FEI and then Thermo Fisher. And then, as you know, in the more recent history, the very big change occurred with the introduction of the single electron counting cameras. That was the really the revolutionary, how do you say, icing of the cake.
So you're talking about how a whole ecosystem really has to be created to support the field. Recently, there has been a lot of growth in public databases. How has that helped intellectually as well?
Well, this is, of course, there was a right at the beginning when the first structures or the first density maps appeared. It was always a big struggle to get maps. Sometimes it took 2 or 3 years. You know, what can now be done in a single day, took a long time. It was very tedious, and then people, try to hold on to the maps to really get all the data mining out of it before they would open up to the public. Okay, so this was a start, and we were told that the same thing happened in X-ray crystallography right at the beginning, that people didn't want to share, but then there was a lot of pressure. And then finally, everybody agreed to share in the same way as X-ray crystallographers did, under pressure from government, pressure from the journals, and so forth. So now we are really, for years now, we are exactly on the same level of data sharing and so forth. So. It was very fruitful when that happened in very big ways in electron microscopy, because people started to deposit their maps, and there was a time when, for instance, flexible fitting methods were introduced, and so everybody could just try out their own tools of flexible fitting with maps that other people had deposited and so forth. So this is all was very fruitful. And then incidentally, the biggest population, maybe it still is in the electron microscopy database, is a ribosome. Okay, and there were, we put a lot of share of ribosomal reconstruction in, but then there were a number of competing groups. And the ribosome is so multifaceted. There are so many things to be discovered that very soon the whole the database was full of them. And now, of course, the situation is changing. There are so many membrane proteins, ion channels, receptors. There's probably there's its own niche now for the COVID related structural results. So there's been an explosion of data, and the sharing is wonderful, including the sharing of original data, of raw data.
So we were talking about how a lot of fields have moved into EM. You were mentioning X-ray crystallography, virology. Are there any fields using EM that surprised you or delighted you?
No, I wasn't really surprised. I mean, it is really, it's very field specific. I guess the big surprise right at the beginning was that it would be a membrane protein that would really come out as a pioneering high resolution structure after the cameras were introduced, because the cards are sort of stacked against it. You have to solve all kinds of other problems, namely to make the the molecule feel like it's in a membrane. So you have to create a lipid environment and hope that the whole thing works. So so it was a surprise to me that that this whole explosion really started with Yifan Cheng's contribution in 2013.
The last question I'll pose before we go to the student submitted questions would be, what are the challenges and opportunities do you see in the field of cryo-EM today?
Well, there's been a lot of exploration of very high resolution, and it's my feeling that these are really, it's not routine to get to a certain level. There's a lot that has to be put together, in terms of instrument specification and software and so forth. So it's not routine, and I think the community will probably level out at a certain resolution that is more commonly achievable, which might be 2.5 or so, and that's really very much depends on the development of pharma. What is the target? What is the expected target for drug development? So I don't think routine achievement of something like 1.5 angstrom is possible or even desirable. It's extra effort beyond a certain point that only consumes a big amount of resources. And so, but the challenges are, what can be additionally achieved. I'm working in 2 areas that I think have promise. And one of them is time-resolved cryo-EM, which allows us to image short-lived states in the rather in the range between something like 10 millisecond and 1,000 milliseconds. And we have the ambition to go down to 1 millisecond so that it becomes available also for ion channels. And the other development is uses the very large amounts of data in the hundreds of thousands and millions range that are available in order to explore the energy landscape of a molecule. And so this can be done by sort of deep data mining techniques. And I've been in a collaboration with someone in Wisconsin, a physicist in Wisconsin, to explore this. So these two things are, I think, are very exciting possibilities that bring us beyond the current pretty much routine techniques that have been developed.
Wonderful. So I'm going to shift to the student questions. Also, students, if you have questions and you don't mind posing it to yourself, let us know in chat and we'll unmute you. Okay, so the first question we had submitted was, when did the resolution revolution start with you or for you? Was that when you got a new detector or new software?
No, it really started. It started when we got a detector, and at the time I was still Howard Hughes Medical Institute investigator, and HMI very generously provided all the people who were, all investigators who were in electron microscopy, which was maybe 5 or 6 people, provided them immediately with this detector. So they didn't, we didn't have to write applications or so. We just got it right away. So we were the first ones to get this in 2012. And so we were really at the front with the development, and but it so happened that the software that was required to take full advantage of this was really driven by other people, including Yifan Cheng, whom I mentioned before, and then Nico Grigoriev. So there were people who really threw all their energy into doing all these fancy averaging and aligning algorithms that are necessary to take full advantage of the movies that you collect.
In terms of single particle cryo-EM, what developments in sample preparation do you believe have been most instrumental?
Well, I can't really point at anything single. There have been developments in all fronts, Spottyton and so forth, where sample preparation has become more automated. Now there is one single contribution was really spectacular, which really comes from NYSBC, from your people, which was the discovery of where the particles are actually sitting, and it was always speculated that they were somewhere comfortable inside of the ice. But then it was discovered by electron tomography that the large majority of the particles were actually sitting at the air-water interface. So that had really a lot of implications. It meant that the specimen preparation, as we know it now, is really not optimized. It really damages the proteins that we want to image with a high likelihood, and so these discoveries Noble, Alex Noble, right, really led to the investigation of how can we shorten the time that the molecule can actually explore all the different environments. And so now I think now the consensus is that we have to go to the times that are shorter than 150 milliseconds or so to ensure that we don't have all the molecules on the air-water interface.
There has been a lot of development from Laurie Passmore's group and Chris Russo on grids. Do you have an ideal grid type? Because the standard grids may or may not be the best form factor.
Yeah, I completely forgot before about the contributions of that group and the introduction of gold grids was something that really took everybody immediately with, and and then the most recent discovery by Chris Russo, I think is going to have a very big impact, and it will lead to the design of different grids. And I can't say anything better than what he already discovered. So he has certain ideas of making the grid square smaller, and and he used an hexagonal ordering rather than a square, and all this is in order to create more stability than was previously provided for the sample. And then he shows that this really has an effect for the for the initial interaction with the beam. And this is sort of very complicated to get into, but I hope that will be covered in your course.
I'll give you, guest lecturer, a right to pass on any question I pose if you don't want to answer it. But this question is, how has commercialization helped or hurt the field of cryo-EM?
Well, this is sort of complicated. Without commercialization, we wouldn't have cryo-EM. There had to be very big investments and certain gambling in coming up with instruments. And one of the really first successful instruments, Polara, almost didn't make it. It was just the pressure by somebody, the energy by someone who made it happen. And because it was a gamble, they didn't know what the market was, and it was a very successful gamble in the end. It was a very big. That was the first big success stories for FEI. So in other words, without commercialization, nothing would have happened at all. But we have still the unique situation that we have one single vendor. I mean, it's not completely true. There's another one, but it has always been limped behind because of the reasons that I told you before. And it's a very unhealthy situation where the whole market is controlled by one vendor, which really means that the prices are controlled. The whole diversification of instruments is controlled. The service market is controlled. The service contracts are so steep that they produce challenges for researchers. So and as well as for resource centers. So this is the bad aspect of it, and I've been praying for other vendors to come along and be strong and challenging, and maybe it's not going to be the the companies that we've heard of. Maybe it's one that simply comes out from a garage somewhere.
So shifting towards analysis and optimization, when you're comparing data sets, how important do you find B factor is? So if you collect several different data sets and you're trying to improve, how much do you use B factor as a criteria?
I'm really not sort of the I'm not using electron microscopy day for day. I don't know how people approach this, and I mean the B factor is obviously a quality indicator, and I would always, if I were confronted with data, I would always prefer the ones with a better B factor. But sort of individual decisions on how to what to do with a data set that is not optimized in this way, whether to throw it away or whether to integrate it with others, that these are all decisions that people have to live with and go with.
Hard decisions to be made by the researcher themselves.
Right.
So in terms of signal to noise, in terms of a normal map, what types of signal to noises are we looking at an electron micrograph? And if we were able to increase the signal to noise, how much would we be able to gain in terms of resolution or detail?
Well, the signal to noise is tied to the ultimate resolution in a very complicated way. First of all, the 0.1 signal to noise ratio is something that we measured a long time ago, and I don't know whether it has much improved. Maybe it has doubled through the introduction of the camera of these cameras that we've been talking about. But the way signal to noise ratio is tied to the resolution is indirect, because it really enables a better alignment, and because we have all these processes in image processing in which raw images are compared with one another, including alignment and classification and so forth. So everywhere you can, the signal to noise ratio determines the tolerances, the error margins, and but these are different for molecules of different sizes. So again, in signal to noise ratio means less for large molecules than it means for smaller ones. Okay, so you have an entire range of improvements from almost no improvement at all to very high improvement, depending on what the size of the molecule is.
Along the lines of resolution, I believe this question is along the lines of Rado Danev came out with some information as he was working on G protein coupler receptors on how to routinely collect mid 2 angstrom reconstructions. And one of the recommendations were to collect as close to focus as possible. So how much does the focus and CTF correction really impact the final resolution? If we were collecting, not just close to focus, but let's say 2, 3, 6 microns defocus, would there be appreciable loss?
When you go to small defocus, you mean?
Or very, very defocused.
Very, okay. Well, and you mentioned Radov, but we're not talking about faceplates right now, right?
No.
No, okay. So so as you as you go closer to focus, you know that the normal CDF is particularly bad in the lower spatial frequencies, and then it if you if you aim at the right spot, at the sweet spot, then you get a very large transfer, the Scherzer focus transfer, and so you know, theoretically you get better alignment, more accurate alignment, since you catch higher spatial frequencies. But there's a whole range of low spatial frequency components which are really dearly needed for alignment, and so you can really by only using the high spatial frequency ones, you can get into error traps. You can get into wrong alignments. So so I'm really I think you would need something like a two focus collection, which is actually a strategy that was introduced a long time ago, to do two collections of the same field at two different focuses. And one of them is where the contrast is very strong, and where you have a lot of components that you can use for alignment. And then the other one would supply high resolution information.
Let's shift towards algorithm development. How has that really helped single particle? And there's been an advent of incorporating machine learning techniques. Do you think that will have equivalent impact as well as, let's say, maximum likelihood has on the field?
Well, you know, we've all seen the power of machine learning algorithms, and they certainly will have a function. And I don't think that they have a function in structure research per se and in interpretation, but rather in all these mundane aspects that, like particle picking and so forth. I think particle picking is already happening, where we have much more powerful algorithms than we had before. And this can only get better. And there's also, I want to bring this up because maybe that's not so much appreciated. We are throwing a lot of particles away, and they are on the level of on the step of particle picking, and and that is sort of a very subjective area, how much we throw away and what criterion we use. But this is very it's very important that we get quantitative right there, not because of the quality of reconstructions, but because in time resolved Cryo-EM, we have the capability of doing kinetics simply by particle counting. We look at subpopulations at different steps, and then we know exactly, you know, how many fall in a particular category, exhibiting a particular structure at a particular time. Now, if you really want to be serious in doing kinetics by Cryo-EM, then we have to be quantitative in particle picking already. Okay, so it affects the counting of the subpopulations.
There has been talk about democratization of Cryo-EM, And some people have been talking about 100 kV FEG microscopes, but what does democratization for cryo-EM mean to you?
Well, 100 kV would be a great start, but the FEG really needs to be part of it. And the problem is that the FEG itself is very expensive. So going down with the voltage, and at the same time keeping a very expensive equipment is a problem. So I don't know how this is going to be solved by the commercial companies, but to have a 100 kV variety instrument would be an enormous difference, including the fact that these are smaller. They can fit into a normal lab. You don't have to, create, go into the next story as it happens right now. So it can all be accommodated in a normal research environment, and it is available. It's accessible through NIH grants. The $5.5 million for a for Krios are so out of range that entire universities have to make arrangements and bring departments together as never before in order to come to an agreement.
We have a question in the chat from Greg Schneider. Given the collaborative and open source nature of software development by CCP4 and the like, how do you envision this type of platform for EM expanding versus commercial software development?
Well, I hope it's gonna happen. I don't know to what extent it already takes place. I think the model itself is in people's minds, and then there are people who are actually they are sort of bridging both communities, and there is still and they are involved in these efforts. The commercial ones, we unfortunately we have the situation with patents being put in for methods that are already existing. They are already in there. And it reminds me of this Russian guy who tried to get a patent on the shape of a bottle, okay? The bottle, the idea of a bottle. So I really think this is a very bad development, and I hope that can be checked in some way.
Switching gears a little bit, could you talk a little bit more about time-resolved cryo-EM and what techniques are used today, as well as what timescales are most useful?
Well, I mentioned before that we already have something that works in the range of 20 to 1,000 milliseconds. Before I mentioned 10, but there are certain dead times that make it not possible right now to reach 10 milliseconds. So in that range, there are a lot of molecular machines with domain movements that go through intermediate stages of sort of local energy minima, which really means that they have a certain resting time in the intermediate time, and so these are then accessible. These are short-lived states, and we want to know all of them in order to get to figure out how the machine works. But it becomes really interesting if we could apply these techniques to ion channels, receptors, and then we really need to get into the range of 1 millisecond. And I'm working with someone at the at the Columbia Engineering Department who likes to work on this. And he has really ingenious ideas on how to make it happen. But these are right now all they are in concept. And we're trying to get a grant proposal in.
Back to data analysis, how do you deal with very dynamic systems, systems that just don't have an open or closed states, but just have a continuous conformational change?
Well, if this is a continuum of changes, then we cannot characterize. I mean, we cannot do this by time resolved techniques because time resolved techniques need to have a certain resting time. Some kind of a time that the intermediate exists in its short life. But I mentioned before that there's an ensemble technique available. If we have a very large data collection, then we can really trap molecules in all different states in a continuum of states. And so if you have an equilibrating molecule, so we're not talking about a particular reaction that we're trapped, but rather we look at an equilibrium, a thermal equilibrium of states. Then certain states are just not very well populated, and you would not see them in normal cryo-EM. But if you have a very large data collection, then the chance of finding them becomes larger, and then in the end we have a continuum of states. And then the problem then is how to make use of that information. And there are data analysis techniques, manifold embedding, in which these conformational changes, the multidimensional conformational changes, can be essentially mapped, and from that you get essentially an accounting of molecules in all its different states. You can enumerate how many molecules are in each state. And if you have such an enumeration, then you can derive the energy landscape from that, because the molecules that you observe only rarely correspond to regions of high energy, and the ones where you observe it very often correspond to minima of the energy landscape. And so in the end, you can really see some kind of a complicated valley in the energy landscape, and from that you can infer how molecules can reach one state from another state.
Could you speak a little bit more about the challenges of processing very large macromolecules? For example, the ribosomes have a lot of, beyond ratcheting, a lot of different conformational changes. So how would perhaps manifold embedding or other techniques help? Also, I guess corollary to that, there is an issue for angular sampling as you get larger and larger molecules when you're trying to process it.
You talk about challenges that come from processing large molecules.
I guess I can go both ways, small or large, both have separate challenges.
Yeah. So the large ones, at least they have a lot of signal, uh, and then obviously all the different processing, the arrays need to be sufficiently large. The searching ranges have to be calibrated. But the large molecules really pose the problem very often that you have a floppiness on the periphery. You have less resolution on the periphery, and much of that heterogeneity really is associated with function. So you want to really have an account of all these different states, and that can be in the case of the ribosome, or you can get a very large number of different classes that come from the same sample, and then you have to relate them to one another. So despite the fact that we are now can process data so quickly, then the interpretation can be the interpretation on the background of existing literature can be very, very difficult. And there you can get into weeks and weeks and months of contemplation, how to make sense of this. And that's really an area where I don't expect artificial intelligence will give us a handle.
Okay, well, I'm at the end of my question list. Does the class have any additional questions? I don't see too many more in the chat, but just in case there are any last minute questions, Joachim, do you have any final words for the students here?
Final words. Well, welcome to the club. I'm really gratified that there's so much enthusiasm, and we have. I just want to tell you that at Columbia we have a very unique situation because we have lots of resources now, and so you have to. You can inform yourself about projects. Maybe you come from someplace at Columbia, but there are lots of opportunities right now to jump right into the to whole opportunities. So what else to say? Well. If you want to, if you happen to be interested in these, in the more far-reaching developments that I mentioned, we can talk about this later, and I could point you in some directions. The time-resolved direction is particularly interesting right now. I think it may be possible to develop this into a technology that really is sort of on everybody's desk, like today, the VitroBot. So there's, it might be possible to get to this place. I have a business, a small business grant together with a commercial company, and we're not getting any profits from this, but we are sort of the academic arm of that company. And for the commercialization of a time-resolved apparatus. So with some luck, we're going to have some prototype in a couple of years that would then be able to be used.
Okay, wonderful. Thank you very much. If there are any last minute questions that you think of after the class, you could always email me and I'll forward them over to Joachim. But otherwise, thank you very much for coming and thank you for interacting with us.
Okay.
So for students, don't forget Wednesday is Journal Club. So we'll see you on Wednesday.